A focus on radian measure.
What is a radian? An angle with its vertex at the center of a circle with radius r that intercepts an arc on the circle with length r has a measure of 1 radians, sometimes written as 1 rad. So we're looking for another way to measure angles. So let's say I have this angle right here. I'm going to go ahead and call it theta. I'm going to say that theta measures 1 radian if the radius, so here I'm going to call the radius r, if the radius is exactly the same as this arc length that the angle intercepts. So this length here is also r. If that's true, if the radius is exactly equal to the arc length, then we say that theta equals 1 radian. Theta is equal to 1 radian. So you can see that word radius involved in radian because we're saying that we have 1 copy of the radius here along the arc of the circle. So now let's go ahead and take a look over here. Let's say I want to find an angle of measure 2 radians. So what that means is that my angle has to intercept an arc length that measures 2 copies of the radius. So here's my radius here, and so this is 1 copy of r, and then this is a second copy of r. So I can see 1 copy of r, and then a second copy of r is occurring. So that means that the angle that we're talking about here is this angle theta. So theta would be equal to 2 radians. Theta would be equal to 2 radians. So we can see if I go all the way around a circle, so here we've already had 2 copies of the radius, this would be a 3rd copy, doesn't quite make it halfway. Then we have a 4th copy of a radius, the 5th copy, a 6th copy of the radius, and I have a little bit extra, So I would make it around a full circle 6 times with the length of the radius, but then have a little bit extra to spare. Radian measure. An angle in radians is measured as the ratio of 2 lengths, the arc length over the radius. So if I want the measure of an angle in radians, I would simply take the arc length divided by the radius. So for this example, they're the same. The arc length is r, the radius is r, so that's 1 radian. In this example, I have the arc length is 2r, and the radius is r, so the measure of this angle here, we would call it theta, is 2r over r. The r's cancel, we end up with 2 radians. In this example, we're looking for the measure of this angle here, call it theta. So the arc length is only half an r, and the radius is r, so that ratio, 1/2 r to r, the r's cancel, we end up with half a radian. For this last one, we're looking for the measure of an angle theta that makes 1 complete revolution, goes all the way around. So we're going to call that angle theta. So we need the arc length. Well, the arc length is just the circumference of the circle. So the circumference is 2 pi r, and then we would take the circumference over the radius. So 2 pi r over r, the r's would cancel, and we get exactly 2 pi radians as the measure of the angle in radians that makes 1 complete revolution. But why do we use radians? As the ratio of 2 lengths, the radian is a pure number that needs no unit symbol, so we consider it unitless. The symbol rad is usually omitted. So unless the degree symbol is used for an angle, it is implied that the angle is in radians. So it's usually at this point where I get asked by students, can I just convert everything to degrees? I prefer degrees. Please don't do this. Since radians are real numbers, remember it's a ratio of the arc length to the radius, so it's unitless, radians have a wider applicable use in engineering and science, so it is important to have a working understanding of them. Understanding how to find angles in radians. Sometimes students struggle with radians because of the fractions involved, so let's do a little bit of review. Let's say we wanted to understand the notion of 1/4. So what we would do is consider a whole split into 4 equal parts. So here I have one square split into 4 equal parts. So if I wanted 1/4 of the square, I would shade one of those 4 equal parts. So now I have the concept of 1/4. Let's apply it to a different shape. So here I have one circle, or almost circle, divided into 4 equal parts. So if I go ahead and shade one of those 4 equal parts, then again I have the concept of 1/4. But instead of a square or a circle, we're going to do a non-traditional shape as the whole. Let's say I consider one semicircle as the whole, and I want to split this into 4 equal parts. So I can think about it as a pizza. So I would go ahead and cut it in half, and then cut each of those halves in half again. So let's say this was a whole pizza that was delivered, and I want to split it into 4 equal parts, so these are my 4 equal parts, so 1/4 would be one of these 4 slices of pizza. So I have 1/4 of the pizza, and then this would be 2/4 of the pizza, and then 3/4 of the pizza, and then 4/4 of the pizza, which simplifies to just 1, and the 2/4 of course simplified to a half. So I just want you to go ahead and keep that in mind as we go in and take a look at our radians. So here on our circle we can see that our angle measures in degrees go up by 45 every time, and students tend to be comfortable with degrees, but we want to be just as comfortable with radians. So the key is to remember that one complete revolution is 2 pi radians. One complete revolution going all the way around is 2 pi radians. So that means going halfway around must be half of that amount. So half of 2 pi is 1 pi. So if I go over here to 180 degrees, that's exactly the same as 1 pi radian. So traveling the top half of this circle, traveling a semicircle, gets us to 1 pi radians. And we want to break that down even further here. So we can see that the top half of this circle is broken into 4 equal parts. So this first angle measure here, which is 45 degrees in degrees, we would think about as 1/4 of pi in radians. So we can see this 1/4, but pi has to be included because the top isn't just simply 1, it's 1 pi radians as an angle measure. So I'm traveling 1/4 of the way, so I have 1/4 of pi, and then I'm traveling 2/4 of pi, which reduces to pi over 2, and then I go a little bit further and I travel 3/4 of pi, and then finally I end up at 4/4 of pi, which is just 1 pi. And I can continue on adding that 1/4 of pi every time, so I end up with 5 pi over 4, 6 pi over 4, which in lowest terms is 3 pi over 2, 7 pi over 4, and then concluding, going all the way around, was going 8/4 pi, and 8 over 4 reduces to 2 pi, which we knew one complete revolution is 2 pi radians. Now let's go and take a look at the circle again, but focusing on angles that increase by 60 degrees every time and understanding those same angles in radian measure. So again, the whole entire circle is 2 pi radians going all the way around. So that means that the semicircle, the top half of the circle, is half of 2 pi, so we end up with that 1 pi radians. But here, if we're focusing on breaking this up at 60 degrees and 120 degrees and then getting to 180 degrees, that's taking even thirds. So I'm traveling 1/3 of the entire 1 pi that makes up the top of the semicircle. So I'm taking 1/3 of that whole pi, or 1/3 pi, and then I'm going another third of the way to end up at 2/3 pi, and then finally 3/3 pi to end up at 1 pi. And then I can continue on. So I have 4/3 pi, 5/3 pi, and 6/3 pi as I move around the circle. So this is just looking at a different set of angles this time and how we'd have to do different subdivisions, how I'd have to create this idea of these different fractions. So now I'm thinking about 1/3 of the semicircle on the top. And this last one, looks a little hectic, but it's because we're now thinking about the 30-degree angles, going all the way around, going up by 30 degrees every time. So if I want to take this whole region here from 0 to 180 degrees and go up by 30 every time, I'm breaking this up into sixths. So if I shaded one of these regions here, that's 1/6 of just the top. So remember, I'm just considering the top because the top is the whole, 1 pi. That's just the top of the circle. So this portion here would be 1/6. So that means this angle here in radians is a 6 pi, and then 2/6 pi, or pi over 3. We have 3 pi over 6, or pi over 2. 4 pi over 6, or 2 pi over 3 reduced. 5 pi over 6, 6 pi over 6. And then I can see as I continue around, 7 pi over 6, 8 pi over 6, 9 pi over 6, a lot more subdivisions, 10 pi over 6, 11 pi over 6, and finally 12 pi over 6, which is 2 pi. So now let's take a look side by side. So here we have the familiar degrees. Remember, 1 complete revolution measures 360 degrees. And then side by side, with all the same angles measured in radians. So remember, 1 complete revolution measures 2 pi radians. So traveling all the way around, I start at 0 degrees, and then I've traveled 1/6 of pi, then 1/4 of pi, 1/3 of pi, and 1/2 of pi, because remember, pi's right here. So up here is half of the way. I've traveled half the way. And then 2/3, 3/4, 5/6, and then a whole pi. Moving along to 7 pi over 6, 5 pi over 4, 4 pi over 3, then 3 pi over 2, or 1.5 pi. So remember, this is 1 pi, so this is 1.5 pi, 1.5 pi. And then 5 pi over 3, 7 pi over 4, 11 pi over 6, and getting back to 2 pi. So in these examples, we're going to determine the quadrant the angle will lie in, if any, and sketch it. So we have theta equals 5 pi over 4. We want to know, where is 5 pi over 4? In which quadrant? So I'm going to go ahead and start a sketch here. So I'm going to go ahead and remember the quadrantal angles. So I have 0, I have 1/2 pi, I have 1 pi, and I have 3 pi over 2. So it's kind of like remembering 0, 90, 180, 270, 360 in degrees. So 5 pi over 4, well, what I'm going to remember here is that 1 pi, that's the same as 4 over 4 pi. So I need to go an extra fourth. So 5 pi over 4 is going to be right here. So I need to connect that. So I have, this is 5 pi over 4. So it's going 1 pi and then another fourth of the way. That is my angle theta. So the answer here, the quadrant, is quadrant 3. And now for beta. So beta is negative 5 pi over 6. So remember, negative means that I travel in a counterclockwise direction. So we'll go ahead and again start to label our quadrantal angles. So I'm going to start at 0. I'm going to travel in a counterclockwise direction. I'm going to label this as negative pi over 2, or negative 1/2 pi, and then negative pi, negative 3 pi over 2. So here, I want to think about everything broken up in sixths. So this is negative 1 pi, or it's negative 6 over 6 pi. And if I want to rewrite this so it has a denominator of 6, I can do that as well if it helps me. So this is negative 3 pi over 6. So negative 5 pi over 6 is between negative 3 pi over 6 and negative 6 pi over 6. So I'm going to break up quadrant 3 into 3 equal parts, because here I have negative 4 pi over 6, and then here I have negative 5 pi over 6. So I'm traveling in that counterclockwise direction to find theta, and I'm again, for angle beta, in quadrant 3. So now we look at angle alpha, 8 pi over 3, And hopefully we can recognize this is more than 1 complete revolution. 8 over 3 is greater than 2. So in fact, I'm going to think about this as an improper fraction. So this is the same as 2 and 2/3 pi. So I'm going to go around 1 complete revolution, that's 2 pi, and then I'm going to go a little further, I'm going to go 2/3 of the way. So if I go ahead and sketch this angle, so I'm going to go ahead and once again label my quadrantal angles, and I know that I go all the way around, that's 2 pi, so there I am so far, and then I have to go 2/3 of the way. So remember, this is 1 pi, so I want to break this down, this top part down, into equal thirds. So this is going an extra 1/3 of the way, and then this is going 2/3 of the way. So 8 pi over 3 is going 2 pi and then 2/3 of the way. So over here is my 8 pi over 3 angle. Right, this is alpha, and that happens to be in quadrant 2. And then here we have gamma is equal to 9 pi over 2, which again is going around more than 1 complete revolution. So how many is it exactly? Well, 2 goes into 9 4 times with 1 left over, so it's 4.5 pi. So that means I'm going to do 2 complete revolutions. 4 pi is 2 complete revolutions, and then I'm going to go an extra half a pi. So here, if I go ahead and construct my angle, so I have 0, a half a pi, pi, 3 pi over 2, and then let's recognize this is the same as 2 pi, it's also the same as 4 pi. So to sketch my angle, I'm going around 2 pi, then another 2 pi, so that was 4 pi, and then I'm going a half a pi. So I'm actually up here along the positive y-axis, so this is my angle gamma, and it's not in a quadrant. It is a quadrantal angle. This is a quadrantal angle. It is not in a quadrant. So now let's see how to convert between degrees and radians. So we'll start by converting degrees to radians, and to do that we multiply by pi over 180 degrees, and then we simplify. And the reason we can do this, we can multiply by this, is because this is basically 1. Remember, pi is equal to 180 degrees. But we'll see what happens. So convert from degrees to radians. Which quadrant will the angle lie in, if any? So we'll go and start with 105 degrees, and we multiply by pi over 180 degrees. And the reason for that is because now the units of degrees will cancel. So I have 105 pi over 180, and we'll reduce to lowest terms and get 7 pi over 12. So this is the same angle in radians as 105 degrees. And 105 degrees is in quadrant 2. So I will absolutely admit that finding the quadrant an angle lies in is a lot easier to identify in degrees and radians. But here, 7 pi over 12, we should get some number sense. Well, 7 over 12 is a little bit bigger than 6 over 12, which is a half a pi. So if I'm a little bit bigger than a half a pi, then that would bring me into quadrant 2. And then here I have the angle 249.8 degrees. So we want to turn that into radians. So 249.8 degrees times pi over 180 degrees. Again, my units of degrees will cancel. So that means I will have radians. So I have 249.8 pi over 180. Which is kind of an ugly looking answer, so I'm actually going to approximate this answer. So keep in mind that pi is the irrational number that continues on forever, 3.14159, etc. So I'm going to substitute this into my calculator and get the approximation 4.36. So 4.36 radians. So sometimes students get really caught up on, oh, it doesn't have a pi in it, so it's not in radians. But remember that a radian is the ratio of the arc length to the radius. And so that ratio is just a real number. So it can have a pi in it and be exact, or we can approximate the value in this case and get 4.36 is perfectly fine. It is still in radians. We just want to make sure we don't put a degree symbol on it. That would mean a completely different angle measure. And then what angle will this quadrant lie in? 249.8 degrees is between 180 and 270 degrees. So this is in quadrant 3. Now we'll convert from radians to degrees. So we multiply by 180 degrees over pi, the reciprocal, and then simplify. So here we'll go ahead and start by looking at 2 pi over 3. So we have 2 pi over 3 and then times 180 degrees over pi. So we can see that we're going to be left with degrees in our answer. So we're going to have 2 times 180 divided by 3, so that's 360 divided by 3, or 120 degrees. And 120 degrees is between 90 and 180, so we are in quadrant 2. So now, if our answer has a pi in it, the other way we can convert to degrees is to simply replace pi with 180 degrees. So another option was to take 2 times 180 degrees over 3, and we would still get 120 degrees out as our answer. But we could see here in part B that we have 4.25, and this is in radians, right? It doesn't have a degree symbol, so it is in radians. So to convert this, we do have to multiply by our 180 degrees over pi to introduce the degree symbol, to introduce the units of degrees in. So here, I'm going to multiply this all out and approximate the answer. So I'm going to multiply 4.25 times 180 divided by pi, and that's approximately 243.5 degrees. And that's between 180 and 270 degrees, so we are in quadrant 3. Now let's review some applications involving radian measure. First, arc length. To calculate the length of an arc S with central angle theta measured in radians, we use the formula S equals R times theta. So here's a visual representation of what we are finding. We are finding the length of the arc S. Here's my central angle theta and my radius R. So we multiply the radius times theta, provided theta is in radians. We can also find the area of a sector. To calculate the area of a sector A with central angle theta, again measured in radians, we use the formula A is equal to 1/2 R squared theta. So here we are finding the area of a part of a circle. So here we're calling this a sector of a circle, and we need the central angle theta in radians and the radius R to be able to calculate the area of the sector. Let's look at an example. Given a circle with central angle theta equals 140 degrees and diameter 12 inches, find the arc length and the area of the sector that correspond to the given angle. So first thing I have to recognize is that the angle I'm given is in degrees. So to use the formulas, I have to convert the angle theta to radians. So I'm going to go ahead and start by saying, well, theta is 140 degrees. So I'm going to go ahead and multiply by pi times 180 degrees. And now degrees will cancel, and I'll be able to reduce this, so I can cancel the degrees. They're both divisible by 20. So I'm going to get 7 over 9. So I get 7 pi over 9 as my angle theta in radians. And on this particular problem, I'm given the diameter of the circle, not the radius, but this is simple. We just divide the diameter by 2 to get the radius. So I'm also going to go ahead and say that the radius here is equal to 6 inches. So if I have the angle in radians and the radius, I can go ahead and find the arc length and the area of the sector using my formulas. So S was equal to R times theta. So my radius is 6, and I'm going to go ahead and put the units too, 6 inches. And then my theta is 7 pi over 9. And this is why it's so important to use radians, because radians are unitless. So we wouldn't want to have degrees here. That wouldn't make sense to have inches degrees. So now we just have inches. So we're going to multiply just the 6 and the 7. So we end up with 42 pi over 9 inches. So this is my exact answer. If I wanted to, I could go ahead and approximate this, right? Because I can approximate the value of pi. But we'll just go ahead and leave our answer exact here. And then we'll find the area of the sector. So the formula was 1/2 r squared times theta. So we have 1/2. Here we have 6 inches as the radius. I'm also going to include the units. And then theta was 7 pi over 9. So now we have 1/2, and then 6 inches squared becomes 36 inches squared. And then we have 7 pi over 9. So we have our units as inches squared, which makes sense because we're talking about area. And then we just need to go ahead and simplify the values that we have here, right? So 9 goes into 36 4 times. So on the top we have 4 times 7, which is 28 divided by 2, or we could have divided 4 and 2. So we have 14 pi inches squared as the area of my sector. Let's take a look at one more example. The minute hand of a clock is 4 inches long. How far does the tip of the minute hand move in 40 minutes? So this problem has a little bit of context to it. So let's draw a picture and think about what's happening here. So we have our clock, and we're told that the minute hand is 4 inches long. So I'm going to go ahead and sketch out that minute hand here, and we're told that that's 4 inches long. So essentially we've been given the radius of my circle, the radius of my clock. And we're being asked how far does the tip of the minute hand move in 40 minutes. So we're thinking about what is this length here, right, all the way to 40 minutes. So 40 minutes would be here, right? So this would be 40 minutes. So we're thinking about this arc length. Let's see if I can get this highlighter going. This arc length here. So I need the central angle. That's all that's missing. I have the radius, but I need this central angle here. So we need to think about, how far this initial side has traveled to get to this terminal side. We're creating this angle theta that's here. All right, so 40 minutes out of a total of 60. So essentially I'm going 2/3 of the way. So I'm going to go ahead and say that, I'm going 40 minutes out of a total of 60 minutes. So I'm going 2/3 of the way around a clock. And I know that an entire revolution is equal to 2 pi radians. So in other words, my value of theta is 2/3 of 2 pi. So I've gone 2/3 of the way, because 40 minutes out of 60 minutes reduces to 2/3, and I'm taking 2/3 of the complete revolution around a circle is equivalent to 2 pi. So in other words, I have an angle theta in radians of 4 pi over 3, right, of 4 pi over 3. And I have the radius in inches, so now I'm just going to go ahead and find the arc length, right? So how far does the tip move? That means the arc length. So S equals R times theta. My radius was 4 inches, and my theta is 4 pi over 3. So we're looking at 16 pi over 3 inches is how far exactly the tip of the minute hand moves in 40 minutes. Another application involving radian measure is linear versus angular speed. Suppose that an object moves around a circle of radius r at a constant speed. If s is the distance traveled in time t around this circle, then the linear speed, v, of the object is v equals s over t. So let's pause there and review what's happening. So what we're saying is that we're focusing on a particular point on a circle. So the circle has a radius r. I'll go ahead and label that in my picture here, closer to the radius. So this is my radius r, here's my point. And if this object or this point on the circle moves at a constant speed, so it's going around the border of the circle here, and we're interested in finding the linear speed is the arc length, right? We call that s, so the arc length divided by the time that has passed. So the linear speed is the arc length over time. So linear speed is v, is a dimension of length per a unit of time. So I have, this is like a distance over a time. And this should sound a little bit familiar because v is a speed, so it's a rate. So we're maybe used to this in a slightly different way, like distance equals rate times time. But all I'm doing is solving for the rate and dividing by the time. So linear speed is coming from this familiar formula that we know, distance equals rate times time. We're just moving things around a little bit. So it's the distance traveled by this point on the outside of the circle over the time that has elapsed. Now, angular speed. The angular speed, omega, of this object is the angle theta swept out divided by the elapsed time, t. So omega is theta over t. So the difference here is that instead of thinking about the linear distance traveled on the outside, we're thinking about how much this angle theta has changed over time. That's angular speed. So this angle theta is clearly growing as I move this counterclockwise direction here. So we're interested in how much that angle is growing as time has passed. So angular speed, omega, is given in revolutions. So we're talking about that angle theta in revolutions per unit of time. So we have this amount of change in the angle over the time elapsed. Right, that's the difference. So we have the distance, so that's the change in how far I've traveled over time versus the change in the angle over time. And there's a relationship between these two, which, I mean, there should be because we're talking about the same circle. The relationship between linear and angular speed is the following, that linear speed, v, is equal to the radius times angular speed, is equal to the radius times angular speed. So here, one of the best things I can try to help you understand this with is to think about a tire. So if you're fixated on a point on the edge of a tire as this tire is spinning, the point on the tire has a different speed. If I think about the tire rotating, that point on the edge has a different speed than if I focus on the hubcap and the little grooves between the hubcap and I focus on the angle. How fast that angle is changing is different than how fast this point on the outside is spinning. They're related because they're on the same tire and that tire has the same radius, but they're not the exact same speed. Let's take a look at an example. A child is spinning a rock at the end of a 2-foot rope at a rate of 180 revolutions per minute. So I'm going to go ahead and draw a circle here because if I'm spinning a rock at the end of a rope, then the shape I'm creating as I'm spinning is a circle. And if the rope is 2 feet long, then what I know is that the radius of that circle is 2 feet. So I'm imagining there's this rock at the end of the rope. So there's like that point on the circle. So I have this rope and it's spinning around and around and around at a rate of 180 revolutions per minute. So the rate that I've been given there is the angular speed of the object. So how do we know it's the angular speed? Because the units are revolutions per minute. So it's not a linear measure. So think of a straight line we measure in inches or in feet or in miles. We are given a rate that has revolutions. That's how far I go in a circle over and over again. So 180 revolutions per minute. So I've been given omega is 180 revolutions per 1 minute. All right, I'm going to write it like this. Find the linear speed of the rock when it's released. So it's like right now I know that the angular speed, right, so how fast this theta is changing is 180 revolutions per minute. But I want to know the linear speed, like right when I let go, this rock is going to shoot in a linear direction, right? If I let go, it's just going to go ahead and take off in a straight line. And how fast will it be going in that straight line? So there was a relationship between linear and angular speed. So we had v is equal to r times omega. So the linear speed v is the radius times the angular speed. Well, the radius was 2 feet, and the angular speed was 180 revolutions per 1 minute. So here I can go ahead and multiply the 2 times 180 and I end up with 360, but I have 360, I have feet times revolution per minute. And this is not the units of linear speed. A linear speed is a distance over a time. Feet is a distance and minute is time. But we need to get rid of this revolution here. So what we want to go ahead and remember is that 1 revolution, so I'm going to do this reminder off to the side. What do we know about 1 revolution? Well, 1 revolution around a circle is either 360 degrees or it's 2 pi radians. Well, I don't want to use degrees because I don't want to introduce another unit that I don't need. I want to replace 1 revolution with 2 pi radians because radians are unitless, right? We can essentially ignore them. So I'm going to replace revolutions, right? This is 1 revolution with 2 pi radians. So I end up with 360 feet per minute, and I'm replacing this revolution with 2 pi radians. But I'm putting the radians in parentheses because remember, radians are unitless. So now I can go ahead and multiply 360 times 2 pi. So we have 720 pi feet per minute as my linear speed. So the moment I let go of this rock that this child is spinning, such a weird problem, I am aware, but as soon as we let go, the speed that that rock is going to travel when it shoots off linearly, right, in a straight line, is going to be 720 pi feet per minute. If, again, this is an exact answer. In this example, we have an object is traveling around a circle with a radius of 2 meters. If, in 20 seconds, the object travels 5 meters, what is its linear speed? What is its angular speed? So we don't need to draw the picture here, but let's go ahead and do it anyways, just to really think about what's happening. So we have, again, this object. It's on a circle with a radius of 2 meters. And we know that in 20 seconds, the object travels 5 meters. So this object that's on the circle, in 20 seconds, it goes around 5 meters. So let's just say it's going in this counterclockwise direction. We have been given, essentially, its linear speed. And we know that it's the linear speed because the units are a linear unit of distance, meters, over a unit of time, seconds. So I have essentially been given v, my linear speed, is, remember, a distance, so we have to put 5 meters in the numerator, over a time, 20 seconds. And then we can go ahead and reduce 5 over 20 is 1/4. So this travels 1/4 of a meter per second. That is the linear speed of this object as it travels around the circle. But now I want to go ahead and find the angular speed. So now we're interested in, if I focus on an angle here, how fast this angle is moving in revolutions per unit of time, in this case seconds. So we had that relationship, right? We had that linear speed is r times angular speed. So we can go ahead and substitute in 1/4, I'm going to include the units, meters per second, is equal to the radius, 2 meters, times omega. So we are going to go ahead and solve for omega. We're going to divide by 2 meters. So I'm going to reorganize this left side a little bit. This is 1 meter in 4 seconds. Right, I'm just choosing to think about this slightly different because when I divide by 2 meters, I'm going to have 1 over 2 meters. And the units of meters are going to cancel out. So far we have angular speed is 1 over 4 seconds. And that kind of sounds weird, and that's because it is. It's 1 radian, right? Because radians are unitless. But what we need is we need it to be revolutions per second, right? That's how we measure angular speed. So we need to think about how do we get rid of radians and turn it into revolutions. So let's write what we know. We know that 1 revolution is equal to 2 pi radians. So the conversion factor here is that if I go ahead and think about dividing this by both sides by 2 pi, all right, dividing both sides by 2 pi, 1 over 2 pi revolutions is equal to 1 radian. So it's similar to how we converted between degrees and radians, right? If 180 degrees is 2 pi radians, then we were able to use that conversion. So we're doing something similar here. 1 revolution is 2 pi radians. So 1 over 2 pi revolutions is 1 radian. So I can replace this numerator here with 1 over 2 pi revolutions. So here's what we have. I'm going to go ahead and work this direction. So I have 1 over 2 pi revolutions, that's in the numerator, over 4 seconds. So now I have my revolutions per second. I have a revolution over a unit of time. I just need to clean this up a little bit. So 1 over 2 pi, and I should be really careful about this. The 2 pi is all in the denominator of the 1. So if I write it slanted like that, I really have to use parentheses. Otherwise, I'd have to write it vertical. So 1 over 2 pi like this, just to be incredibly clear about where that pi is at. So here, 1 over 2 pi divided by 4, we can think about multiplying by the reciprocal. So 1 over 2 pi times the reciprocal 1 over 4 is going to give me 1 over 8 pi. And then we have revolutions per second as my angular speed. Okay. So it's really just about recognizing linear speed is a distance over a time, and angular speed has to be a revolution over a time, and knowing the relationship between 1 revolution and 2 pi radians.